Hi, my name is Yunong Liu from the Department of Medical and Molecular Genetics. In this module, we will continue to discuss NGS data format. This is the second module about that topic. We'll discuss SEM and BAM files. Refresh your memory a little bit. There are three standard formats for NGS data. The FASTQ file, which is raw sequencing data, the SEM or BAM file, which is the sequence alignment data, and the VCF, which is variant data. So we'll go through the second part, SEM or BAM files. The SEM and BAM files, they are actually the same thing, except for the SEM files are the text files that we can read, we can edit, we can look into it, and BAM files are the binary format, which can be only read by the machine. So let's go through the individual elements in these files and to see what are the information being contained here. The initial publication of the SEM and BAM files can be found in this 2009 bioinformatics paper, and I recommend you to read this paper for a little bit more details. But in general, the SEM and BAM files, they are generic alignment formats, support either short and long reads, support pair ends, support different sequencing platforms, and we talk about there are many different sequencing platforms. They're very flexible in style, compact in size, and computationally efficient to access. So we go through the individual topics to talk about the individual elements. There is a reference documentation of this file format, which you can see from this website, and has a very detailed instruction what individual field means. Again, the BAM is a binary format representation of the SEM files. So let's dive into the detail. What are included in these files? There are two components of this file. The top part is the header. So we'll go through that very briefly. And the bottom is the alignment information. The so-called alignment is if you got one sequence raise, remember that next generation sequencing technology give you many of those, millions to billions of sequencing rates. But for every single sequencing rate, that we need to find out where they came from the reference genome. And this SEM and BAM file are the file format to record that. So the alignment component, the bottom part, is where those sequence arrays aligns. Let's start from the header. The header is the basic information about these files that will include many different elements. So for example, HD, and which is the file information, it tells you the SEM or BAM file format version, and sorting order of the alignment is that based on the genomic location or based on the other information that are in these sequencing arrays. The SQ tells you the reference sequencing information. For example, is this mouse genome or human genome? If it's human, is this HG19 or HG38? So those are very important information that we need to record in the reference information. RG, read group information. Normally this will contain which sequencing center this data is being produced, the date is produced, the flow order and the library information, and so on and so forth. PG is the program information. So when we do any sequence alignment, normally it starts from the FASTQ files we went through in the last module, and then run some of the programs to do the sequence alignment. Which algorithm are we using to generate this alignment information, and which version of that software is? So those are all very important documentation that we need to dive in when we read these SEM and BAM files. And all this information are being included in the header sections. And also, there is options to provide additional text information, text comments of this. All right, so now let's go into the real data And this is one of the data that we have generated in our sequencing center quite a long time ago. And this is just a brief screenshot of it. And as you can see, there are many different lines here, and each line corresponding to one specific sequencing read. So let me zoom in a little bit. So this is just one of the lines. And you can see there are many individual fields available. The first part is in this part. It's this part. So this part, now let's zoom in to individual line. Now let's zoom into individual line. In this particular line, and this is one sequencing raise, as you can see, now let's dive into individual lines. And this is a zoom in version of one line here. As you can see, there are many different elements. So let's go through these elements one at a time. We will start from this part. And this part, as this table shows, it is a query name, which is the query name of the sequencing read or read pairs. Remember, when we talk about the FASTQ file, the first elements, the first line in the FASTQ file is a sequence identifier. In this part, normally, this will be the sequence identifier. And it is unique for every single read on one specific flow cell, and that records which sequencing rates it represents to. The second part is a flag information, and it's a number, and we will go through that in a little more detail. The third line is quite straightforward. There's the chromosome information, where this particular race, the chromosome it maps to, and then the position information of this particular read aligns to. And then there's a mapping quality information. So we will go through those mapping quality in the future as well. And then there's a cigar strain and the mate reference name. So this is in the pair end situation that we know that there are two reads in this alignment files, and one read is the same is the name is query name, and what is the name of the other end of the read. And normally it will be the same as the reference name, so that will be just it's an equal sign here. And after that will be the position of the mate position, and then the inferred insertion size. So it goes through this inferred insertion size as well, and the sequence information, as you can see, and the quality information. So remember that these are the information that will be in the FASTQ file as well. Essentially, actually, if you look at these files in a little bit more detail, you will find that BAM file actually contains all the information of the FASTQ files if you decided to include all this information in the BAM file. And in the FASTQ file, this will be the sequence query name and the reference information, the nucleotide sequences, as well as the quality information. So sometimes that people stop storing FASTQ file actually, because FASTQ files are text format, they take a little bit more space. And some people just convert that into the BAM file, and then you can make it a more compact binary format and then distribute the BAM file. So that is a quite a normal practice in recent days. And there are specific tools that you can use to convert the BAM file into the FASTQ file. All right, So now I will give you one example to show what our individual element means in this file. And this is one of the toy example that is being published in this bioinformatics paper. So I will go through this with you individually. Again, these are the formats that we mentioned in the previous slides. And these are actually one of the examples that they provided. So you can see I break it down into detail. The top part is the reference genomic location as well as the reference sequence. And this part are the sequencing rates that in reality, where they align to. And the bottom part here is going to be just the BAM information and to record where the sequence aligned to. So let's go through this individually. All right, as I mentioned earlier, for the first part, it's pretty straightforward. It's just the sequence identifier, whatever the sequence identifier being reported in the FASTQ files. So the first element I want to go through is this particular flag files. And as you can see, some of these numbers are zero, and some of them are not zero. So let's go through this. 163, what this really means. This sounds like just a number, but actually this number contains a lot of information in that. So before we get into detail, I want to just reassure you, this is just for your knowledge. Normally, we do not read these numbers. The machine has a program to read this, but the reason I want to present this to you is you have a general idea what are the information being recorded in this particular number. So let's see what 163 means. Actually, 163 can be converted into this binary data, 00010100011. If you do the binary converter, you will know this is real. Okay, so what in reality, how do we operate is going to be from bottom to top, and then to line up this number 000 and 101000011. So this is exactly the number of 163. So remember, this is representing read number 1. Okay, so what this really means, now we have this table to check the meaning. The first line here, 1, that the description is the template having multiple fragments in the sequencing. So as you can see, this number is 1. What this really means tells us is, yes, to answer this particular question, this description, and the answer is yes. And which means that in addition to this nucleotide read, there is another read from this fragment in the BAM file. So what that really tells us is this is a paired end raise. So which means there are 2 read that coming from the same fragment. All right, the second one, each fragment properly aligned according to the liner. And the answer is yes. That means both this particular read and the pair end read are both properly aligned. Next one is fragment is unmapped. That is no, because it is being mapped. So you see it's 0. Next one, next fragment in template unmapped. So this is 0 because it is mapped. And the next one is a sequence being reverse complemented. So what that means is we know that we have a human genome that we have the DNA sequence here, and this read is being reverse complemented. The answer is no, because it's 0, and that means this read is coming from 5' to 3' end of the genome. And that tells you this particular read is from 5 to 3. Next one is a sequence of the next fragment in the template are being reversed. And the answer is yes, which means the other read is somewhere from 3' end to 5' end. And next one is the secondary alignment. And so we don't have to worry about all those information. And you can see that the first fragment, is this the first fragment in the template? The answer is 0. That means this is not the first fragment in the template. What that really means is the initial DNA sequence actually is the fragment you want to sequence is from 3' end to 5' end. That's why this particular read information is from 5 to 3 at the same time. It is not the first fragment in the template. Well, the next one is this the last fragment in the template? The answer is yes. So you can see this is the initial DNA fragments, and then this is the second read of that particular fragments. So overall, when we put all this information together, we will know this is a pair end, both ends aligned, and this is again, this is a paired end, and this is the second read in the pair. If we put all this together, and this is what we learned about this sequencing race, the initial DNA fragment is from 3' to 5', and then this is read 2 in this fragment, so that is from 5' end to 3' end. And then if you look at the location of this, and it's starting from fragment number, nuclear position number 7. And this is this 163, just one number, what it tells us. This is very, very compact information that with this number contains a lot of information. So let's go through another one, and which is this particular one. This is 83, okay? And you can see that for the read identifier, it is R001. Clearly, this is the same read of this particular one. It is a pair end, so both ends are being documented in this particular file. What 83 is, if you convert the 83 into this particular number, it will be 000010100011. This is 83. So you can see, you can read against this table as well. But what it tells us, if you look at here, this is the difference between the two read. In this case, is a sequence being reverse complemented, and the answer for this one is 1, which means it's yes. So you can see the sequence is reverse complemented. It is from 3' end to the 5' end. And then the next one is this one, is this first fragment in the template. The answer is yes. So this is the first fragment in the templates. And then by reading the position of this, you'll be able to appreciate where this particular read aligned to. So based on this information, we will have a rough idea of the organization of this sequencing race and from this particular field. As I mentioned earlier, the third field, which is reference genome, this is pretty standard. So we know this is in this case, the toy example, there's only one reference genome, so it's called REF, and sometimes it calls chromosome 1, chromosome 2, and that is in our normal alignment format. And the next one is the position, the genomic position. This sounds like a pretty straightforward number to align there, but actually there is something that we need to pay attention to. This the real concept is that there is two levels, two different type of definition of the this genomic location. For example, there is a one base coordinate system and a 0 base coordinate system. So what that really means is for the one base coordinate system, And the first base of sequence is 1. And the region is a closed interval. For example, if I say from the 3rd to the 7th, 3, 4, 5, 6, 7, from the 3rd to the 7th position, and then you will say, I'm looking at from the 3rd nucleotide to the 7th nucleotide. So it's a closed interval. Well, for the zero-base coordinate system, oh, by the way, that the one-base system, the SEM file, GFF, and other file formats are using that. For the zero-base coordinate system, it's the first base of the sequence is considered as 0. And as a matter of fact, what it points to is the number of the gaps that you are pointing to. That's why that a region is a half closed and half open interval. For example, the region between the 3rd and the 7th nucleotide is from here to 3, 4, 5, 6, 7, from here to here. So which is the second gap all the way to the 7th gap, and this is representing the nucleotide rays that coming from the 3rd to the 7th nucleotide. So you started from 2. So that is the major distinction of this two coordinate system. So we need to pay attention to that for a specific file format, which coordinate system the file are really using. Otherwise, and you will read this file and get one base pair shift of your reading. So that will not be a good thing. Okay, so the next file format is 30, as I mentioned earlier. It is a mapping quality that is reported by sequence alignment, so we'll not go into detail about that. So the next one is the SEM and BAM file. In this is this particular field, and that is the cigar strain. So what you can see from here is there is quite a different combination of the letters and the numbers, okay? And then actually the letters really means something. M means match or mismatch. I means there is an insertion. D means deletion. H is hard clipping, and S is soft clipping. There is some distinction between hard and soft clipping. I'm not going to go too much detail. And P is paddling, N is skip. So let me give you an example so you know what this really means. It's taking the first sequencing read as an example, which is here. So you can see that in this read, and it says started from, let's use the next slide on this. So it's a little bigger. So the first read here, it is 8M. And if you look at read number 1, there is a 8 base that is being perfectly aligned to the reference genome. So that's why we're putting 8M here. The next one is 2I, and that means there is a 2 base insertion. What that means is in the reference genome, there is no such nucleotide, such base, but in this particular individual, there is a 2 base in this case as an insertion. So that's why there's 2I here. And the next one is there is a 4 more base of a matching. And so that's why you see 4M. And then there's 1 base deletion here. So that is 1D and followed by 3 base of M, matching again. So based on this particular one, cigar strain, you will know this read, how this is being aligned into this position. So the previous one, the position information, it only tells you where it aligns to, but it doesn't really tell you the alignment quality or any measure like that. But the cigar strain will tell you that. And I will give you another example, which is this particular one, and reference 004. So you can see this is the alignment is. And then you see, you read this is 6M. That is straightforward. 6 base here. And there's a 5M towards the end. And then in the middle, there is a 14N. That N means there is being skipped. So there is not insertion deletion, instead it's being skipped. This happens a lot in the RNA sequencing alignment. So keep in mind when we do the RNA sequencing, we are sequencing the mature messenger RNA. At least that's our intention. But when we map a read from the mature messenger into the reference genome, sometimes they will cross the junctions. So one end in one exon, the other one in another exon, and that leave a big gap in the middle. So sometimes that we will, if we see a really large N here, and that is the indication that this is the RNA sequencing rate, and the middle part is the junction rates. So again, that the definition is being defined in the previous slides. If you're interested, you can learn a little bit more detail about that. Okay, so now let's jump to this particular one, the inferred fragment size. So what that really means, this is a field that is only for paired end. If it's a single end read, like the other reads other than this particular 4 and this 2, and they are all being zeros, as you can see. The number, so this inferred fragment size is the number of bases from the leftmost mapped base to the rightmost mapped base of the original sequencing fragments. So let's taking this R001 as example again. All right. So remember that when we discuss about this 163 and 183, these two numbers, and we know these sequencing rates are being aligned in this way. So in this way, you can see that R001 started from position number 7, while R001 on the reverse side of it ended or start, you can consider that, at the position number 45. And then what this really tells you is the fragment size between this is 39 bases. So this tells you the fragment size of this particular sequence alignment of the original DNA molecule that you are trying to sequence. If this is for the leftmost race, in this case, it is the R001 plus here, it is a positive number, and then for the second rate, this will be the negative number. So that is pretty much all the confusing information that are being documented in these SEM and BAM files. And I think, again, the point here is not trying to make you remember everything being presented here. Instead, just appreciate what are the information are being included in the SEM and BAM file, and then you will see that whether you have to use certain bioinformatics tools or you need to do a little bit of programming and to look into what the data is. So there are some optional fields for the SEM and BAM files, actually quite a few of those. And they are all being presented in this particular format, tag, and the type and the value. So one example is shown here, NM, colon, I, and 2. So NM tells you what this field represents to. I tells you this is the integer number, and then 2 means it is 2. So I know that NM represented additive distance, which means how many bases your sequence is different from the reference genome. And in this case, for that particular one, if it says NMI2, that means this particular read is aligned to this position on the genome, but there are two bases that is different. That is what that means. And actually, there are many predefined fields of this particular format. I talked briefly about NM, but there are many others as well. And they are actually growing because the BAM files are being evolving as well. And sometimes to increase the freedom or customization, that this field can be user-defined as well. So I'm just putting a few of those important fields there that you can go back and read this in a little bit more detail. For example, AS stands for alignment scores that being generated by the aligner. So remember that in the BAM file, there is an alignment quality field. This is different because some of the alignment algorithms prefer to calculate another score, and this will be documented in those three fields as well. Okay, and the CM and the NM are how different your read compared to the reference genome. Those are considered as edited distance, and there's others as well. So I'm not going to go into detail. There are many such individual fields that are available. Oh, by the way, this OC and is super important, and this is the original cigar strain, and then why we need this, because when we do the sequence alignment, sometimes we will do the sequence alignment and we will need to refine the alignment. So basically it's a two level of alignment. In that case, we may need to record that what are the original cigar strain alignment is, and then document the cigar strain for this particular alignment. And there are many others available. Again, that BAM file is the binary format of the SEM file. So they are more compact, it's easier to transfer or download or store in your hard drive. And also there's another very important feature is it's indexable. So what that means is if you need to, let's say if you have very big BAM file, maybe 50 gigabytes of a file. If you say, okay, tell me the reads that align from here to here, and if you have to go through every single read, you'll be in trouble. But because this file is indexed, so that you can very quickly to say from chromosome 1, from this location to this location, give me all those reads, and this can be retrieved very, very quickly. So you don't have to go through individual reads about that. And that is a very, very important feature. We use that very constantly. And as I mentioned earlier, these files are being updated very, very frequently because of the involvement of the next generation sequencing technology. So the most updated information can be found in this particular website. There's more information, a little bit more I want to talk about is there are a lot of recent extensions about the BAM file because of the single cell technology. So you can see that these are the tags that is specifically associated with the single cell technology. For example, what is a cell barcode? What is a cell barcode read quality? And so on and so forth. I'm not going to go into detail, and the UMI information. So those are very, very important. So when we do the single cell data analysis, we still pass the data with this standard alignment format, which is either SEM or BAM files, but we will be able to retrieve the information that we need. For example, give me all the reads that are coming from this particular cell. How are we going to do that? I will check the cell barcode and say, with this particular cell barcode, what are the sequencing rate that associated with this cell barcode? Bring them out. Okay, I can create a smaller cell type. For example, when you do the single cell again, that you say, okay, here are the cells that make a cluster. It looks like epithelial cells, and this is something that I'm very much interested in. So give me all these cells. How do I do that? I will need to know what barcode associated with these cells and pull them out and to generate a smaller BAM format file that represent that specific cell types. All right, so that's all I want to talk about today about this BAM and SEM files. As you can see, this is very intensive and a lot of information are there. And I think if you need to doing specific data processing, this is something that you have to understand what are the information being stored here. And I hope you enjoy this, and I hope this will be being useful. And in the next module, we'll go through the last standard file format, which is the VCF file that represent the variant information.